uh, chapter 12, in which we will see how to design a short column, that is uniaxial and biaxial both. Okay, design of short column under compression with uniaxial bending, that limits state of collapse. Okay, uh, there can be two cases: one when the neutral axis falls inside the cross section, and another when the neutral axis falls outside the cross section, right? So first we will see the case 1, distribution of stress and strain on the column section when the neutral axis falls within the cross section of the column, that is eccentricity E is equal to mu by pu is sufficiently high to induce some tensile strain in the column section, right? So when the neutral axis is within the section, then you will have some portion under tension and some portion under compression, right? Only when the neutral axis is at the face of the column, then there will be no tension and the column will be under total section will be under compression, right? Okay. So in this case, this is the concrete design curve which we will use for finding the internal force due to concrete, right? Concrete design curve, that is FCC. This is very similar to that we use in flexure member, and this is the strain diagram which we will be using. The ultimate strain on the compression phase for the concrete is taken as 0.0035, and on the other phase it will be 0.0035 into d minus xu divided by xu. Okay, now coming to the second case, distribution of stress and strain on the column section when the neutral axis falls outside the cross section of the column, that is eccentricity E mu by p is small and whole cross section is under compression. Okay, so you can see over here the neutral axis is outside the column section. So in this case, your concrete design curve will be something like this, right? It will be something like this. It will be something like this, right? And the strain diagram will be something like this. Okay, code says for such cases the strain at the compression phase to be taken is 0.0035 minus 0.75 into EU. EU is the least strain on the other phase, right? Least strain. Okay, so this strain will always vary between 0.0035 and 0.002. Now this is the point which acts as a pivot or fulcrum, you can say. This is at a distance 3 by 7d, and the strain over here will remain constant, that is 0.002, whatever may be the location of the neutral axis, right? So when you move this neutral axis far, then this strain will decrease and this strain will increase, right? And when the neutral axis is found to be at infinitive, then you will find that the strain over the whole cross section will be 0.002 uniformly distributed over the whole cross section. Okay, that is what we have already studied in chapter 11 part 1, right? Okay, so over here we can see the design curve of for the concrete will be something like this, that is like this. Okay, so doing the design with such type of stress curve is very difficult. So code has made our life easy and has suggested that you can take an average stress diagram, right? So over here the design stress is 0.447 FCK. Instead of that, you can take X FCK and you can find X FCK X by this formula. For finding X, you will require G. You can find G by this formula. And once you know your X, you can, now this is the uniform strain acting over the whole cross section, right? So your force FCC will become X into FCK. So this will be X into FCK into D into B. Okay, and that will give you force FCC, which will be acting at a distance J, which can be found by this formula. Okay. So when you are taking this design curve actual, then we know that our FCC falls at a distance 0.416 XU. But now we are taking an average stress diagram, so we have to find the distance of the CG from the compression phase of force FCC, and that is found by this formula, that is equal to J, right? Okay. Now let me tabulate above theory in a table. Okay, when XU falls within the column section, so this is our design stress, concrete design stress type, which we are very familiar, which we have used many times in design of structure member. Okay, FC, that is FCC force, is 0.362 FCKB into XU, right? And now we know in seeing this figure, we know that the stress between from strain 0.002 to 0.0035 is going to be 0.447 FCK, and after that the stress varies parabolically. Okay, so if you know the strain, you can find the stress, right? Just put the value of strain in this formula, okay, and you can find the corresponding stress for corresponding to that strain, right? So this is the case when neutral axis falls within the cross section. You can find FCC using this formula. Simple. Okay. Now, when your neutral axis falls outside the section, then you have to first find G, then X, then J, and you can find your FCC using this formula, which I explained. Okay. This is your average stress diagram over here. So this, instead of 0.447 FCK, it will be X FCK. X you have to find from here, right? So X FCK into D into B, that will be your force FCC, okay, which will be acting at a distance J, okay. So when the neutral axis falls outside the cross section, then for finding FCC, you will have to use this formula. Okay, so these are very important points which we will be using our designing a column. Okay. Now coming to the next point, that is regarding steel, right? Now how to find force in the steel? So let us take a column. I am taking a column, okay, and I want to find the forces in the steel layers, right? So I am viewing this column from this side. Okay, so this is layer 1, and layer 1 has two number of steels. This is layer 2, and layer 2 has two number of steel bars, and this is layer 3, and layer 3 has two number of steel bars. Okay, I am viewing this from this direction. So this is my layer 1, this is my layer 2, this is my layer 3. Okay, there are two number of bars in layer 1, there are two number of bars in layer 3, there are two number of bars in layer 3. This layer 2, this layer 3, right? Fine. So let us try to understand that how do we find the force in the steel layer. Okay, now first of all, now let me assume that my neutral axis is at a distance 200 mm. Okay, fine. So this is my concrete design curve, right? This is force FCC. Okay, now this steel layer is under compression, and this two will be under tension because the neutral axis is falling over here, right? Okay, now this is the table A, okay, which will be used number of times. Silent point on the design stress strain curve for cold work bars, right? So this is I have taken from SP16. This table is obtained from the design curve for FE415 and FE500. Okay, these are the different stress levels. These are the strains. These are the corresponding stresses. Again, strain and corresponding stresses, right? Okay, fine. So over here, this column, okay, our FE is 415. Okay, so now first thing is that we have to find the strains, right? You can make a table like this. Okay, layer 1, layer 2, layer 3. Area of steel in layer 1, that is area of this two bar is say 625 mm. Area of this two bar in layer 2 is again say 625 mm. Okay, 625 mm. And layer 3, again you have two bars, and okay, layer 3 you have two bars, and the area of that two bars is again 625, right? Now we have to find the strain. Okay, so when the neutral axis is within the cross section, we know that we will be using this strain diagram, right? The strain on the compression face is 0.0035 and strain on the other face is 0.0035 into d minus xu divided by xu, right? Okay, fine. So that is what I have written over here. Okay, strain over here is 0.0035, strain over here is 0.0035 into d minus xu divided by xu. Okay, so from the principle of triangles, you can find the strain over here, strain over here, strain over here, right? So strain over here is 0.0026, strain over here is 0.0009, strain over here is 0.0044, right? Once you know the strain, you can find the stresses, right? Our is Fe415, so we will use this table. Okay. Now one important point. Okay. Now once you find the strain, then you have to find the stress, right? So when the bar is under compression, okay, then in that case, the stress in steel is to be taken as Fi obtained from the table, Fi obtained from the table minus 0.447 FCK, okay, when the bar is under compression, okay. So the final stress in the compression steel ASC is Fi minus 0.447 FCK, where Fi is deducted from a value of 0.447 FCK, which is the stress due to concrete area replaced by the area of compression steel ASC. This is very important, right? So in compression zone, when we are providing compression steel, some area of concrete will be replaced by this area of compression steel. And to handle that, okay, the stress of concrete has been deducted from the stress in steel. Okay, that is why when the for compression steel, you have to deduct this stress due to concrete from the stress obtained from this table, right? That is why Fi minus 0.447 FCK is to be taken in account, right? Because some concrete is replaced by this steel area, right? So okay. Okay, when it is a longitudinal tensile steel, then whatever value you get from the table has to be applied. You do not have to detect 0.447 FCK, because in case, because of the assumption which we have taken in account, that in tension zone we neglect concrete. Okay, so that is why we do not have to deduct 0.447 FCK from this in tensile steel, right? Okay, fine. So we know this is under compression, this is under tension, this is under tension. So for this steel, we will apply this formula, and for these two steel layers, we will apply this formula, right? So the strain over here in this layer is this, okay? So 0.026 falls between these two. Find the corresponding stress, that is your Fi, minus 0.447 FCK is your final stress, that is 339.39, right? Now find the stress in this, right? Strain is 0.0009, so that falls somewhere over here. You can find the stress by interpolation between 0 and 288.7, and that is directly taken because the longitudinal it is a longitudinal tensile steel, right? So no deduction is to be made. Whatever stress we get away from here is written directly over here, that is 175.43, right? Similar, this is also a steel layer in tension. Okay, so this is 0.0044. So 0.004 is greater than 0.0038. So code says when your yield strain is when the strain is greater than yield strain, okay, or equal to yield strain, then the yield stress will be 360.9. Okay, so that is why you already 360.9. So once you know your stress, you know the area into stress will give you force, right? So this is the force acting over here, and this is the force acting over here, this is the force acting over here. So this is how you find the forces in steel layer. So now we have learned that how do we find the force in concrete, and how do we find the force in steel. Okay, so now we will be using this for design purpose. Okay, fine. Interaction design curve. Okay, interaction curve. The PM interaction design curve is a complete graphical representation of the design strength of a uniaxially eccentrically loaded column for a given section. Each point on the curve corresponds to ultimate load Pu and ultimate moment Mu associated for the specific location of the neutral axis, right? So here we can see different points are shown over here. So for different depth of neutral axis, you get a unique value of Pu and Mu, and which are plotted. Okay, so when you join this, you get a PM interaction diagram, and that curve gives us the ultimate load and ultimate moment carrying capacity of the section at different location of the neutral axis, right? Okay, fine. Now there will be a balance section. Okay, balance section is that section where steel and concrete yields together, right? So that the eccentricity at that is taken as E balance, right? Now if your actual E is less than E balance, then it will undergo a compression failure. What is compression failure? Compression failure, when E is less than E balance, yielding of the longitudinal steel in tension does not take place, and failure occurs due to crushing of concrete at the highly compressed phase. Okay. Now, if your E is found to be greater than E balance, then the column will undergo a tensile failure, right? What is tension failure? When E is greater than E balance, yielding of outermost longitudinal steel yields first, and then successively inner rows and on the tension side starts yielding. Finally, failure occurs when concrete at highly compressed phase gets crushed, right? So say this is your compressed phase, this is your tensile phase, then this steel layer will yield first, then this steel layer will yield, and then this steel layer will yield, and finally this concrete will crush and the column will fail. Okay, so this is known as tensile failure. Okay, so let us start with an example. Let us try to learn that how can we develop a PM interaction diagram curve, right? So this is chart 48, compression with bending, rectangular section, reinforcement distributed equally on four sides, right? So I am going to take this graph, okay, this graph, okay, this graph, sorry, this, okay, this graph. So FCK is 20, Fy is 500, P by FCK I am taking as 0.1, right? This is 0.1, okay. So area of longitudinal reinforcement, okay, we can find by this formula, that is equal to 2500 mm square. Okay, so I'm going to use 20 mm dia bar. So this divided by area of 20 mm dia bar is going to 8 numbers. So I'm providing 8 number of 20 mm dia bars, right? Okay, I'm using this graph because my d dash by d ratio is 1.1, right? My d dash is 50, my d is 500, so 50 divided by 500 is 0.1. So that is why I am using this graph, right? Okay, fine. So now we will take we will find the ultimate load and ultimate moment, that is Pu and Mu, for the different locations of the neutral axis. Okay, so first we will take sorry, first we will take our neutral axis is assuming that it is at a distance 150 mm from the compression phase. So this is our compression phase, so the neutral axis is say at 150 mm somewhere over here. Okay, we are drawing this PM interaction diagram about the major axis, right? That is why we are taking D as 500, right? Okay, fine. So we are assuming that our neutral axis is at 150 mm. Okay, so for that case, this is our concrete design curve. Okay, this is force FCC, this is force FCC. We have three steels layers, right? I am viewing this section from this side, so layer 1, layer 2 and layer 3. Okay, so this is layer 1, this is layer 2 and this is layer 3. So first let me calculate the steel area. In layer 1 I have 3 numbers of 20 mm dia bars, so area of 3 number of 20 mm bar is 942 mm square. In layer 2 I have 2 number of 20 mm dia bar, the area of 220 mm dia bar is 628. Similarly in layer 3 I have 3 number of 20 mm dia bar, so the area of 3 bars is 942 again, right? Okay, fine. Now the next step is I have to find force FCC that is due to concrete. So I know that my neutral axis is falling within the column section. So I have to simply see the chart, okay, and I will follow this formula, right? When my XU falls within the column section, I have to use this formula for finding FCC. So I'll be finding FCC by using this formula, okay? So my FCC is equal to, okay, FCC is found to be 284.17, right? Now this force FCC will give an clockwise moment about the CG. So that is equal to 52.48. Clockwise is taken as positive, compressive force is taken as positive, right? So this is now, I have completed all the calculations regarding due to concrete, right? Now I have to do the calculations for the steel, right? So first I have to find the strain. Okay, so this is my strain diagram, right? So the strain diagram which I am going to use is as I have explained above. Okay, when our neutral axis falls within the section, then this is a strain diagram which we are going to use. Strain on the compression phase I am going to take as 0.0035, and on the other phase I am going to take as 0.0035 into d minus xu by xu, right? So this is what I'm going to use, right? So this is what I have used over here. Okay, strain over here is 0.0035. Strain over here is 0.0035 into d minus xu divided by xu. So once you know, you can find the strain over here by principle of triangles. Okay, so strain over here is 0.0024. Strain over here is 0.0021. Strain over here is 0.0065. Now please remember, this layer is under compression. These tail layers are under tension, right? So for this layer, we are going to use this formula for finding the stress, right? Okay, for compression, steel under compression will be using this formula, and for steel under tension we'll be using this formula, right? So now we have found the strain. Okay, so the strain is 0.0024, and this is steel under compression. So let us see the table A. 0.0024, our Fe is 500. Okay, so 0.0024 falls between these two. You find the stress. Okay, whatever stress you get, okay, has to be deducted by 0.447 FCK. That will be your final stress FC for that steel layer, right? So that final stress is 387.69. Now these two are steel under tension, right? The strain is 0.0021. So see the table, 0.0021, 0.0021 falls between these two, right? Find the corresponding stress. Whatever stress you get directly is applied to the table, because this is tensile steel. So you do not have to deduct 0.447 FCK, and that stress is 378.23, right? This is now 0.0065. So this is a strain, right? 0.0065. So from the table A, 0.06065 is greater than the ultimate strain, right? So in that case, our yield stress will be 434.8. Okay, so that is what we have to take. Okay, no deduction has to be made because this is steel under this is tensile steel, right? So whatever value we get from the table has to be applied. 434.78, that is 0.8, right? Okay, so once you know the stress into area is force, stress into area is force, stress into area is force. So this force is over here, and this force is over here, this force is over here, right? So this is how we get the force, right? Now this force will give a moment about CG. So that is this moment, positive because clockwise. This will give no moment, so 0. This will again give a clockwise moment. So again, this is that moment, right? Positive because it's clockwise. So when you add all these forces, you get PU. When you add all this moment, you get MU, right? So this is how you get PU and MU for a particular location of the neutral axis. Now this can be plotted on graph, right? So let us see. This is the graph. Okay, whatever P you get divided by FCKPD, whatever M you get divided by FCK BD square, and you can plot it on the graph. So this is our point 1, right? Now coming to the point 2. Point 2, we are taking our neutral axis at a distance 250 mm. Okay. Again, we can see that the neutral axis falls within the section. Okay. First, find all the requirements or all the details required that is due to concrete. First, we will find FCC. For FCC, again, you have to use the same case. Okay, you have to use this case because the neutral axis falls within the section. Use this formula, right? And for strain, okay, you have to use this, right? Because the neutral axis falls within the cross section. Okay, sorry. So this is our second case. Okay, so over here FCC is found from that formula is 452.5. This will give an clockwise moment about CG. So this is the moment. Now strain over here is 0.0035. Strain over here is 0.0035 into D minus XU divided by XU. Find the corresponding strain over here. Over here the strain is 0. Over here, so this strain is 0.0028. This strain is 0 because the neutral axis passes through the CG, right? So the stress and strain over here will be 0, and this strain is again 0.0028, right? Now you can see over here, though the strains are same, strain over here and over here are same, but the stresses are different because this is still under compression. So from the table you get this stress, but that has to be deducted by 0.447 FCK because this is under compression, right? So that is why this is deducted by 0.447 FCK. That is why you get 404.93, and this is directly taken from the table without any deduction. That is 413.93, right? So this is how you get the stresses. Stress into area is your force. Stress into area is your force. Okay, so this is how you get this force. Okay, this force is this force. This force is this force. Okay, now this will give a clockwise moment. Okay, this will give again a clockwise moment, that is this. Okay, clockwise moment means it is positive. Compressive force means it is positive. Tensile force means it is negative, right? So at these forces you get Pu, at this moment you get Mu, and then again you can plot it on the graph. Okay, okay, so this is your point 2. Okay, similarly point 3, point 4. Okay, point 3 is again when you are taking XU is equal to 300 mm. All the formulas are to be used as same above, which I showed you, because the depth of neutral axis is inside the cross section, right? So similarly, add this you get Pu, add this you get Mu, right? Similarly, this is your fourth point. Okay, fourth point I have taken as 500. That is that neutral axis is at the face of the column. Okay, so same formulas has to be used. Okay, okay, let me show you this in detail. So for finding FCC, we will be using this formula. Okay, this is the formula for finding FCC. Okay, so that is what has to be used because the section, the neutral axis does not fall outside the section. Okay, that is why. So for this case, this is your FCC. Now this is your FCC. This will give an clockwise moment, that is equal to this much. Now we can see when our neutral axis is at the face. Okay, so all the steel layers will be under compression. Okay, so this is your force FCC. Now find the strain over here, find the strain over here, find the strain over here. Strain over here to be taken is 0.0035, and over here it will be 0, right? So you can find the strain using principle of triangles. So these are the strain I have obtained: 0.0032, 0.0018, and 0.0004 over here, right? So from the table A, you can find the corresponding stresses, and whatever stress you get from the table has to be deducted by 0.447 FCK in all the three cases, because all the three steel layers are under compression, right? So this is the final stress. This is the stress in this steel layer, this is the stress in this steel layer, and this is the stress in this steel layer. Okay, so stress into area will give you force. So this is the force over here, this is the force over here, this is the force over here, right? Now this will give you a clockwise moment, so positive. This will give you no moment, so zero. This will give you anti-clockwise moment, so negative, right? Add these forces, you get pu. Add add these forces, you get pu. Add these moments, you get mu. Okay, and that can be plotted on graph, and this is your fifth point, right? Okay, now sixth point I have taken is that the load, that the neutral axis is at infinity, right? So in that, sorry, that the last point which we saw was fourth point. Now fifth point is that when neutral axis is at 750 m. Okay, so we can see that when neutral axis is at 750 mm, so the neutral axis falls outside the column section, right? So in this case, now we will be using this formula. Okay, this formula. Okay, XU falls outside the column section. So find FCC using this formula. So find G, find X, find J, and FCC can be found by this formula. Okay, first find X FCK. Okay, once you know X, you can find this will be your X FCK. This is your D, and this is your B. Okay, this is how you find FCC. Okay, so also find J. Okay, J is the distance of the force from the compression phase. This will be your J, right? Okay, so let me return to the problem. Okay, so FCC is found to be 1056.95. Now this is distance J, right? This is distance J from the compression phase, which is found from the formula above, right? Okay, so that is 239.77. Okay, so this will give you a clockwise moment, which is this much, right? Okay, now strain diagram. Okay, the strain diagram will also change. Okay, the strain diagram that which we are going to use will be this one. Okay, this is the strain diagram which now we will use, right? Over here, the strain at the compression phase will be 0.0035 minus 0.75 into least strain. Okay, so this is our least strain. Now, both these strain are found by principle of principle of triangles. We know that at this point, at a distance v by 7d, the strain remains constant, 0.002. Okay, whatever may be the location of the neutral axis, but the strain over here will remain constant. This will act as a fulcrum, or you can say pivot, right? This will decrease, this will increase, but the strain over here will remain constant, right? So from this you can always find you can find the least strain. Once you know the least strain, you can find this as 0.0035 minus 0.75 into it, this by using principle of triangle. Simple, very simple, right? So using this, I have found the strain equal to, okay, over here, right? So this is 0.002 strain. This is our pivot. Okay, you can easily find your EU, and this is equal to 0.0035 minus 0.75 EU, right? So after finding this two, you can find the strain at this level, strain at this level, and strain at this level, right? So this is the strain over here, this is the strain over here, this is the strain over here, right? So again over here we can see all the three steel layers are under compression. So for this strain, find the stress Fy from the table A and deduct it by 0.447 FCK, and you will get the final stresses, right? Once you get the final stress, multiply with area, you get the force. This is the force acting over here. This is force acting over here, and this is the force acting over here, right? This is FCC, this is FCC, right? Okay, so this is how add up all the forces you get PU, add up all the moments you get MU. Okay, and this can be plotted over here. This is point number 5. Okay, now taking the last point, that is assuming that neutral axis is at infinity, right? So we have to use same formulas as for case which we use for point 0.5, and you will see that when the neutral axis is at infinity, the strain becomes constant over the whole cross section, that is equal to 0.002. You can see 0.002, 0.002, 0.02, right? So in this case, moment will be zero, okay, almost zero. So add this forces, you get the ultimate axial load which the column can carry, right? And moment will be zero, okay. So this is how we plotted this point over here, okay. So this is how we draw the PM interaction diagram. Well, to get a more accurate graph, okay, take more number of points. Okay, as many number of points you take, the graph will be more accurate, right? So when you join this, okay, you will get a graph something like this, which is shown over here. Okay, a graph something like this, right? Okay, so this is what we have tried to draw. Okay, develop the PM, that is the PM diagram which we have developed over here, right? Now let us check the results with our calculations. Okay, so this is the graph given in the code. Okay, so let us take the first point, PU and MU. PU and MU for first case is PU is 2.29, MU is 207.44. Okay, so let me show you the table now. Okay, so dividing PU by FCKBD, I get this is 0, and dividing MU by FCKBD square, I get this is 0.1656. From the graph 0, and this is the graph we are using, this is 0.16. Okay, at 0 this is 0.16, we are getting 0.1656, right? This is more accurate than graph, because in graph we cannot get the accurate values, right? Point 2, when PU by FCKBD is 0.117, this is 0.17. Over here we get 0.176, right? When it is 0.38, we get this as 0.14, where over here we get as 0.145. This is 0.629, so 0.63, we get this as 0.08. Over here we get as 0.0828, right? This is 0.74, we get this as 0.036. This is, we get as 0.03588, right? And at infinity, this is 0.81. Okay, we get 0.81. Okay, so this is how we can develop a PM interaction diagram for any type of column, right? Okay, now coming to the next topic, that is design of rectangular short biaxial column. Okay, as mentioned above, all columns are to be treated as being subjected to axial compression combined with biaxial bending, as the design must account for possible eccentricities in loading a minimum, at least with the respect of both major and minor axes. Okay. The specified method adopted by S456 2000 is based on Bristol's formulation for the load contour, whereby the approximate relationship between MURX and MURY is specified. For a specified PUR, which is taken equal to the design load PU, is established. Okay, this relationship is conveniently expressed in a non-dimensional form as follows, right? Okay, So pu is our design load. Okay, so we are assuming that our design load is equal to the ultimate load pur which the column can carry. And for that ultimate load PUR, we find the corresponding ultimate moment carrying capacity of the section about x-axis and about y-y axis. So about x-axis, it is taken, no, it is denoted as MURX. About y-y, it is denoted as MURY. Okay, MURX and MURY are the ultimate load carrying, ultimate moment carrying capacity of the section corresponding to ultimate load carrying capacity PUR, which we take as PU. Okay, so this is formula. Okay, please remember this formula is only applicable to symmetrical sections about major and minor axis. Okay, it can be applied to all the symmetrical sections which are symmetrical about major and minor axis. Okay, so I have explained MUX and MUY are the design moment. Okay, fine. So this is the interaction surface for a biaxially loaded column. Okay, fine. Short column subjected to axial compression and biaxial bending. Most of the column are subjected to axial compression load and moment about both major and minor axis due to the consideration of the accidental eccentricity as shown in figure above. Okay, as a symmetrical section, the factor moment MUX and MUY acting on the section respect to the bending axis, that is about major axis and minor axis respectively, can be resolved in single resultant moment mu, which acts about an axis inclined to the principal axis. Okay, so mu is the resultant of these two, e is the eccentricity resultant of these two. Okay, so you can find mu, and which will be acting about this axis, right? This is the inclined axis, right? And this will be your resultant eccentricity, right? So you can find with this formula, right? Fine. PUZ is the ultimate load that the column can carry. Okay, which is formulated as 0.45 FCK plus into AC plus 0.75 FI into AS. AS is the area of the steel, AC is the area of the concrete, right? So this can be replaced by this way, can be also did this way. PUZ is equal to 0.45 FCK into AG. AG is the gross area. Okay, over here it is AC. Now over here I am using AG. Okay, 0.45 FCK into AG plus 0.75 FI minus 0.45 FCK into AS. Okay, so AS is the area of steel. So this can be replaced by this. I am going to use this formula. Okay, fine. Now how to find alpha n? Okay, alpha n, for this is the graph given in the code. Okay, when alpha n, when pu by puz ratio is less than 0.2, alpha n is going to be 1, right? When pu by puz is greater than 0.8, okay, then alpha n will be taken as 2, right? In between this, alpha n can be interpolated. Okay, you can use this formula 0.667 plus 1.667 into pu by puz, right? So this is how we find alpha n in this is alpha n, right? Okay, so this is your design moment about x-axis. This is the ultimate moment carrying capacity about x-axis. This is your design moment about y-y axis. This is the ultimate moment carrying capacity of the section about y-y axis for the corresponding PUR, which we take as PU. Okay, simple. So now let us okay, very another important point. Sometimes it so happens that a column has two moments, but there is no axial force, right? It has mx and my, but it has no axial force. In that case, pu by puz is taken as 0 and corresponding alpha n is taken as 1. and above formula will turn into this, right? And this is when there is no axial force on a biaxial column, okay, then you have to use this formula, okay, right? That's simple. Okay, problem: a corner column of size 500 by 250 mm is subjected to affected load PUR, which will be considering as this PU, which will be we will be considering as PUR. Okay, PU is equal to 1300, MUX is 100, MUY is 30, unsupported length is 2.9, concrete grade M20, Fe415, and we have to check whether section is safe or not, right? So this is the section which we are going to use, okay. So this is pretty known to us, okay. This is your major axis, this will be your minor axis, okay. This is a mistake, please forgive me. This is minor, this is going to be minor axis, and this is going to be major axis, okay. Please correct me, okay. This is your compression phase, this is your compression phase, okay. We are going to use the same example as we seen above. FCK is 20, Fi is 500, and P by FCK is 1.1. Area of steel is 2500, and 20 MDAV bar we are going to use, so number of bar required is 8, so this is 8, okay. So for this is the graph which we will be using about the major axis, okay, and this is the graph which we will be using about minor axis, okay. So question comes in our mind that why two different graphs, right? Simple, because of this d dash by d in case of major axis. In case of major axis, about major axis, our d is 500 and d dash is 50, so 50 divided by 500 is 0.1, so we have to use this graph, okay. When we are considering minor axis, our d will be 250 and d dash is 50, so 50 by 250 is 0.2, so we have to use this graph, right? That is why two different graphs are used, that is one for major axis and another for minor axis, right? I've written over here about major axis, d dash by d is 0.1, d is 500, d dash is 50. About minor axis, d dash by d is 0.2, d is 250 and d dash is 50, right? So we can make a simple table like this. PU is given 1300, MUX is 100, MUY is 30. So PU by FCKBD is 0.52, right? So we have to find the ultimate moment carrying capacity of the section about XX and Y by axis, right? For the corresponding PU, okay? So this is 0.52. So simple, 0.52 I get, I'm using this graph, right? That P by FCK is 0.1, right? So this is equal to 0.11, so this is 0.11, okay. Now again about my minor axis, 0.52, this is 0.088, so this is 0.088, right? So my MURX will be equal to FCKBD square into 0.11, so that is 137.5. My MURY will be equal to FCKBD square into 0.088, that is 55 kilonewton meter, right? MUX is 100, MUY is 30, this is given to us. Alpha we found over here, okay. PU is, PUZ is given by this formula. This is equal to 2040, right? Now PU is 1300, PUZ is 2040, this is equal to 0.637. Put the value of this 0.67 falls between these two, right? So put the value of PU by PUZ over here and you get alpha n is equal to 1.727, right? Corresponding alpha n is 1.727, right? Simple. So you know all the values over here, okay. Everything is known, put over here. This is equal to 0.927 and this ratio is less than 1, so it is safe, right? So this is how we do the design of a biaxial column, right? Below table shows more precise result from MMS programs software. Okay, so as according to my software, the ratio is found to be 0.914. Okay, this is more precise because in code we do not get the exact values. Okay, because we have to assume some values because it's a graph, right? So this is found to be 0.927 and this is found to be 0.94. Okay, but in both the cases they are less than 1, so the section is safe. Okay, fine. Circular column are always uniaxial. Okay, so please visit website mmsprogramcivil.com for the education videos. This video is also uploaded on website. I hope you must have found this video useful. Thank you.